Hello, in this video I'm going to say a little about wave behaviour. So these are the effects that we encounter when we're describing how waves are moving through space and time. There's 5 of these things that I'm going to run through at a sort of high level. So we've got superposition and interference. This is what happens when more than one wave meets at a particular point in space and time. So how do waves combine together. Then we've got propagation. How does a wave move through space and time? Reflection, what happens when a wave meets a boundary between two different media. It's bouncing back. If it's approaching a boundary in one medium, it reflects back, it stays in the same medium. Refraction is the effect that we see on a wave when it changes speed as it's moving. So sometimes this might be as it crosses a boundary. So if it crosses a boundary from one medium to another, it will often change speed. That will change its direction when that's happening. But you don't always have to change the medium that the wave is in. I mean, we see this in water waves when the depth of the water affects the speed of the wave. So the wave is moving faster in deeper water and then slower in shallower water. So we got different ways that the speed of the wave can change, and then refraction is describing how that affects the propagation. And then we've got diffraction, which is the change in the propagation of a wave when it meets some kind of obstacle or passes through a gap or something like that. So you might have a gap and the wave is then going through this gap, and then it might, it will spread out in some way. Or you might have an obstacle in the way of the wave, and then this is then spreading the wave around the obstacle. It then fills up the sort of shadow region. So we've got these 5 main things that I'm going to be looking at here. I won't cover polarization. Polarization I'm going to talk about in the videos that I'm doing on electromagnetic waves. I know it's not just electromagnetic waves that can be polarized, but I'm not going to cover that here because this is already going to be a long video going through these 5 things. So I'll separate that one off. I'm going to be using some animations in this as well, and I've not created these animations. They've all been created by a chap called Dan Russell, who is a professor of waves and acoustics at the Pennsylvania State University in the United States. So he's quite the waves guru. I'll link to his website in the description below this video. It's worth having a poke around on there. Very knowledgeable chap, knows a lot more about waves than I do, or ever will do. So all of the animations here are his. So there you go on that. So I'm going to push on, talk first of all about superposition and interference. So these 2 terms are often used interchangeably. I mean, we don't really need to get too bogged down in what, if any, difference there is between the 2 of them. I tend to think of superposition being the actual occurrence, the event of 2 waves or more than 2 waves, 2 or more waves coinciding in a certain position in space and time. So we can say that the waves will superpose if they're at the same location in space and time. The waves superpose, and then interference is then the process of combining these waves together, and we're just doing a vector addition of the displacements. So we know on a wave, we've been drawing these out when we were doing our wave profiles. You've got some kind of equilibrium, and a displacement of a particle or whatever it may be on the wave, the displacement away from that equilibrium position can be in either direction. It could be, say, positive direction going upwards here or negative going downwards, but the direction matters. So we need to include that when we're adding up the waves, when we're doing our interference of superposing waves. So we're just adding up then the displacements, and then the combination of all of the displacements added together gives us the resultant wave that forms at that particular point. So this is time for an animation or 2. Right, so here's 2 pulses that are superposing and interfering. So we've got a higher amplitude wave, a larger wave appearing here on the left and traveling to the right. We've got a smaller, lower amplitude wave appearing on the right, I should say, and then traveling to the left. In the middle, they superpose, which gives us interference, and we're just adding them up. So in this case, all of the displacements are positive. They're all upwards. So we're just adding them together, and then you'll see that the resultant envelope is much higher. It gets all the way up here somewhere when the two of them combine, because we're just adding the amplitudes together. So that's a excuse me, a nice visualization of something that you're probably familiar with. Here's another way of looking at interference. So we've got two waves which are the same in every way, except the top one's stationary and the bottom one is moving. So they've got the same wavelength, the same frequency, the same amplitude, but they're moving relative to each other. So say we're moving with the first wave, which makes it look stationary, and then we've got this second wave which has got a relative motion. So we're getting this constant change in the phase happening. Is continually changing, I should say. So a continual change in the phase. So when the two waves are in phase, as in the peaks and the troughs are lining up as we get here, we've got constructive interference, and we get these large amplitudes as we add them together, add the two waves together. But when the two waves are anti-phase, as in when the troughs and the peaks are lining up, so as we're going to get here, then we've got destructive interference. Everything, when you add it up, do your vector sum, it all cancels out and we just get a flat line. So, but because the phase difference is continually changing here, this resultant that we've got at the bottom, the combination of the two waves, is changing all the time depending on what the phase difference is. So this is going to be particularly important when we get on to looking at standing waves and things like that. So we'll be coming back to this effect of interference in later videos. But looking at this first is useful because we can use these ideas of superposition and interference to help us visualize what's going on with some of these other effects, or in fact all of these other effects that I'm about to talk about. So let's go back to think about propagation. So in propagation, there's a couple of things probably worth keeping in mind. First of all, it's worth thinking about what the mechanism is for spreading this disturbance through space. We're saying that a wave is some disturbance in space and time that then propagates through space. So what is the mechanism which is causing this propagation? So it could be something mechanical, like we've got a wave on a string where the tension in the string is what is communicating the disturbance to the neighboring points in space. So because we need something which is going to communicate the fact that we've had a disturbance at some point. So if you disturb a string, then the tension in the string is pulling the neighboring points out of position. We've got some way of communicating that disturbance. It could be the pressure variations in a sound wave, where we're getting alternate bands of high pressure and low pressure and how they're interacting with each other as a sound wave propagates through air, say, or through water, or whatever it might be propagating through. It could be in an electromagnetic wave where we've got an interaction between the electric and magnetic fields. Some disturbance in the electric field creates a disturbance in the magnetic field, which creates a disturbance in the electric field. This is propagating through space according to Maxwell's equations, which we'll get onto in later videos as well. So there's some mechanism behind the propagation. So it's worth thinking about what the mechanism actually is. And then when it comes to describing propagation and these other features of waves, at least in classical physics, we've got the Huygens-Fresnel principle, which is the descriptive process that was used, well, until we moved into modern physics, the descriptive process used to describe waves and how they move around. So we're talking, 18th, 19th century stuff. So say we've got some wave, say we've done the old pebble in a pond thing, we've created our disturbance, and we've got this ripple in the pond. So we've got our first peak here of a wave which is moving out in 2 dimensions, in all directions away here from that initial disturbance. How do we know how this is going to propagate? Well, according to the Huygens-Fresnel principle, we can take every single point on this wavefront. Now, remember these lines, if you think back to the previous video that I did on how we can represent waves, we talked about wavefronts. We can take every point, of which I've marked some on this line that is a wavefront, and treat that as an imaginary new source of propagation, a new source of a wave disturbance. So you can draw little ripples around each one of these circles all the way round. And these we can then consider as superposing and then interfering with each other in order to create the next wavefront. And it turns out that the next wavefront is then the common tangent to all of these individual sort of imaginary little propagations. So that's going to create another circle going around. So we've got our initial circle, treat every point on that circle as being a new source, get those to superpose and interfere, we get the next circle, and then so on and so on. So the Huygens-Fresnel principle, at least if you do it in more detail, it's giving you the new wavefront. It's also describing how the energy is spreading out through space. So it's giving us a descriptive power of how to describe how these waves are moving around. We've got new ways of describing a lot of these wave propagations. If we're looking at electromagnetic waves, this is all in quantum physics and such like nowadays, but that's way beyond what we're trying to do in pre-university physics. So Huygens-Fresnel principle is a good way of visualizing what's going on, particularly if we get on a slightly more complicated wave behaviors. Speaking of which, let's move on to reflection. So this is where we're hitting a boundary between 2 different media, and the wave is then bouncing back into the medium from which it came from. Now, usually when we're thinking of reflection, the first thing that springs to mind is specular reflection. So this is where we're getting a sharp reflection, our angle of incidence is equal to our angle of reflection. This is what we get in a mirror, where we're then seeing a mirror image of something. So it's very ordered, the reflection that we're getting off of the boundary. Now we can get diffuse reflection as well. If you see the sunlight bouncing off of someone's head or something like that, well, you don't see your image in their head unless it's been spectacularly well polished. We're getting more of a reflective sort of glow. It's spread out. It's less organized. We get a lot of this off of, if it's organic matter or something like that, then we're not going to get the same level of organization. We're not going to get a specular reflection. So we've got these 2 different types of reflection here. We can also describe reflection using the Huygens-Fresnel principle. It's a lot harder to actually draw out. But if we've got these wavefronts coming in to this boundary, then when they hit the boundary, if you went through the whole process of going through applying the Huygens-Fresnel principle, then you're going to start getting this reflection. You'd have to draw all of the points out again. You go through all the interference, all the superposition and such like, and then that will help to then describe the change in direction in this specular reflection that's going on here. So it can be applied again. I'm not going to try to draw it out because it is crazily difficult, particularly using this pen on this screen. So one other thing that is worth keeping in mind with reflection, so you don't necessarily need to get too bogged down in all of this, although you might find it interesting and want to look into it a little bit more, is you can get phase changes when a wave is reflected. So particularly if it's moving from a high velocity to a lower velocity, so higher velocity to lower velocity, you'll often get a pi phase shift. So let's go back to some animations. Right, so here we got a wave on a string, say, but the string is in two parts. We've got a heavy bit of string, which is the dark line on the left, and a lighter bit of string, which is the thinner line on the right. So the wave comes in along the heavier string, in from the left, traveling to the right. And it reflects back because it's going from lower velocity to higher velocity. We're not getting a phase change. So you'll see at the boundary between the two strings, we're getting some transmission, as in some of the wave keeps going. And on the lighter string, it moves faster with a higher amplitude, but we're getting some transmission and we're getting some reflection. I mean, this is typical of a boundary between media. You get a bit of both in a lot of cases. You're going to get some transmission, some reflection. You know, we're used to seeing this. It's like if you look through a window, you know you can see what's outside, but quite often you can see a reflection of yourself as well. You're getting a bit of both. Some light is being transmitted, some light is being reflected. We're getting, you know, it's not the same as looking in a mirror. We're not getting total reflection. We're getting a combination of the two. But here, the reflected wave is not suffering a phase shift. It's just reflecting. If we do this the other way round, so we start in the higher velocity medium, so on the lighter string where the wave is moving faster, if we start there, then we can see on the reflection, we're getting a phase shift. So we're still getting transmission, where we're then going to get a slower wave on the heavier string of lower amplitude, and we're going to get this phase shift. Now we see this also when we're, you know, maybe refracting and reflecting, if we've got an air glass boundary, something like that. So when we're then going from the faster medium to the slower medium, so from air into glass, we're going to get a phase shift at that boundary. So this is something you want to keep in mind, at least be aware that it's something that occurs when you're hitting the boundary between two different media. So that's all I'm going to say here about reflection. So on to what we got next, refraction. So refraction is where we've got a change in direction of the wave because it's changed speed. Now, typically we're going to be thinking about this at, say, a boundary. So we've got light, it's going from air, it's going into glass. So say we're drawing our wave fronts here. This is the light coming along here. It hits the boundary. Now it's traveling faster here than it is here. So when one part of the wave has hit the boundary and it's gone into the glass, it's going to have traveled a shorter distance. So it's going to bend off. So we're going to get this bending effect. And then when everything is now moving in the glass, it's moving in a different direction. Like our normal to the wave fronts here is in that direction. And our normal to the wave fronts here is in that direction. So it's changed, it's bent. And it's also changed the wavelength. Remember, the wavelength is the distance between the wave fronts. It's not the length of these lines, it's the distance between them. And the wavelength would have shortened because the frequency doesn't change, that stays the same. Our velocity has dropped, so our wavelength must drop when we move into the slower medium, because remember, the velocity is the frequency times the wavelength. So this is the effect that we're seeing here. We also see it, as I mentioned earlier, as waves move into shallower water. So if you've got waves approaching a beach at an angle, as they move into the shallower water, they're going to bend because they're going to slow as they move into the shallower water. So you're going to get a bending effect going on there. So because waves move faster in deep water because they're not so bothered by what's going on at the seabed, and they slow down as they get into shallower water. So again, you get a change in direction. And this is what we're going to be looking at in more detail when we get onto electromagnetic waves in a video or two after this. Then we'll be able to quantify all of this in Snell's law and put some maths behind it. All of the maths, as you'll see, is lacking in this video because it's just too difficult with the array of waves that we're dealing with. You know, every different type of wave is going to need a different mathematical treatment. So, and we just can't go through all of that in pre-university physics, both in terms of volume of work and the complexity of it. So last up, we've got diffraction. So this is where a wave spreads out when it hits a gap or an obstacle. And again, this is something where the Huygens-Fresnel principle can help. So say that's our gap. We've got some, say it's water waves approaching this. And we've got our wave fronts coming down here. And you'd think, well, okay, we've got this. We've now got this shadow region back here. Well, it's not going to be aware of the waves. Well, turns out not true. If we've got our, we could set up all our little points going along here. We can do our Huygens-Fresnel principle, and we find that the waves spread out by varying amounts depending upon the size of the gap. So if we had, think of this as we have done as being superposition and interference of waves starting from every one of these little points along this line, plus we've got new wavefronts turning up. So if the difference in like the path difference between one side of the gap to the other side of the gap, if that's one wavelength, then by the time the source here has reached the other side of the gap, they're going to be in phase and they're going to constructively interfere. Plus, we're going to have had another wave turn up because everything here is a wavelength apart. The width of the gap, the gap between the wave fronts, everything is a wavelength, and we're going to get massive amounts of constructive interference. And we're going to have this new source here at the edge of the gap, which is then going to propagate everywhere. Because remember, what waves tend to do is propagate in all directions. This is how they spread out. Waves go in all directions. The question here isn't so much why is it spreading out after the gap, it's more why isn't it spreading out before the gap? That's the thing which is maybe of more interest going on here. Why is it collimated here, as in going in a beam? Why have we got this beam here? Because the natural tendency for waves is to spread out. And that's what it does when you put the gap in the way. It's almost like it's reset. Now, if you change the size of the gap, well, the interference between these different sources, according to Huygens-Fresnel principle, is going to change. And you're going to get a different pattern, different diffraction pattern behind this gap. You might get peaks and troughs. It won't spread out in the optimal manner as it does when the gap is one wavelength wide. If it's smaller, you're getting less energy going through. If it's 1.5 wavelengths wide, well, you're starting to get destructive interference when you've crossed the width of the gap. So it all gets into quite complicated ways of combining all of these waves using Huygens-Fresnel principle. But as I say, it's the collimated wave that is unusual. We have to go to some length to get a collimated wave. You might use a laser or a parabolic mirror or something like that in order to focus your beam so it's moving in a particular direction, because usually it's just going to keep on spacing out. To have these even straight line wavefronts, and we can get these, I suppose, from distant stars. Okay, they're circles, but the circles are so big that by the time we see them, we're more or less just seeing these straight lines. So that is the exception, really, to the natural, what you'd expect, at least on short length scales, of how waves behave. So we get a similar thing if you put an obstacle in the way. So you put some block in the way of a wave, and then the wave comes along. Well, you've got a similar thing here in reverse, that we can get waves then propagating around this block because we've got these new point sources on the edges of the block there. So the wave can go round corners, so to speak, and start being felt in the shadow region behind the block. So that's what's going on with diffraction. It's the spreading out of these waves, so sort of reverting to their natural tendency to propagate in all directions. Right, so as I've said at the beginning with all of this, there's been no maths in any of this. It's been all verbally descriptive. It's been a bit hand wavy, and that is because of the complexity and just the vast array of different waves that we encounter. So, but we do need to have an understanding of what these basic wave behaviors are. That we've got a general propagation through a medium, which will tend to be in all directions, unless something is going to constrain it in some way. We need to think about reflection, what happens when we reach a boundary between different media, what happens with refraction when we're changing the speed of a wave and then thereby changing the direction and the wavelength, and what happens when we hit obstacles and then the wave starts spreading out again. So we're changing the direction of the propagation again in a different way. So you need to be familiar with all of those different processes and thinking of it in terms of the Huygens-Fresnel principle. I mean, it did wonders for people in classical physics for ages. So, throughout the 18th and 19th century. So it's no bad place to start. And then if you carry on to study waves at university, you'll be able to get into more complex and more detailed mathematical descriptions of all of this, talking about how a wave on a string will propagate, having the maths behind that, the maths of acoustics and sound waves, the maths and physics of electromagnetic waves. So all of that will come later, but they all need their own mathematical treatment, but they all have these same underlying principles of wave behavior, which I've summarized here. So hopefully that was of some use. And we'll move on to now our case study of electromagnetic waves, where we'll then be able to look at these and put a bit of mathematical substance behind it all, rather than just be waving around in descriptive verbal descriptive terms.